no further ado, welcome Jordan Moore. Round of applause, please.
Cool. Can you hear me? Yeah, it's good. All right, so yeah, my name is Jordan. I'm gonna give a quick little run through about kind of like what the Styx emulator is, kind of how we got here, and then what we're gonna do going forwards, and like what some of the perspective plans are, and like some kind of calls for collaboration and stuff. So this will be pretty fun. So I guess before getting started though, this is software emulation, and emulation is like a very both nuanced and like namespace collision heavy area. So software emulation in this case is saying I have a target program that runs on some sort of processor, and I'm going to emulate that processor so that the software does not know it is not running on hardware. So yeah. So to get started, the real vision here, when we kind of set out for doing this is we need a single kind of like uniform way to interact with emulators. You'll kind of see why in a sec. And we wanted a single emulation API where no matter what the backend is or like what you're targeting, what kind of thing you're looking at, you really just need to use like the same kind of code base or like the same code. So similar to how like Anger has an API where if you want to interact with a bunch of different architectures, cool, you can go do the same thing. And you just switch up kind of your arguments of like, hey, I want to look at an AMD 64 processor or something else. And the big kind of thing here is there's a lot of past performance and like millions of man hours that have been spent into software emulation already. And so we want to create something that does not cause like those like go to waste or like just be like another thing that implements their own separate thing. Like backwards compatibility is kind of like a must here. Yeah. And then we want kind of like the big change here, if you can see my mouse, yes, is we want it to be able to be tailored by users, because some of the issues is that like some of the frameworks out there just kind of give you all the pieces and say, yes, you use our pieces and that's it. And sometimes you don't want to run software, you want to debug it. And that's kind of where Styx comes in. So to kind of a little bit more like sometimes if you want to like emulate a radio, you want to be able to connect it to like MATLAB or GNU radio. If you want to emulate all the components on like a plane or a quadcopter or something, sometimes you might want to toss it into a physics simulator and get real data back. If you're trying to emulate, or like now for some of their like NVIDIA data centers, if you go and you want to say, hey, NVIDIA, I want to buy a data center, they are going to give you like a digital twin physics simulation of what that's going to look like so that you could test out some robotic stuff and kind of get like, this is actually going to be like your power profile. And so it's like, okay, but what about connecting that simulation back into actual like your target code you're going to build? So that's like, we want to be able to do that. And the important thing here is we want to be able to do that with a single tool. There's nothing anywhere right now that does that, except Styx. But and then also it's like kind of going back to the whole we need it to be user tailorable is sometimes there's a new architecture that comes out, or there's a new chip, new peripheral, new radio, new something. And a lot of the current tools and stuff are more designed where it's you are kind of stuck using what the designers and initial maintainers thought of. And if they didn't think of it, you're out of luck. So we need it to be extensible by the users in a manner that is like usable. And we need to be able to let users add it quickly every single time, no matter what it is, on their timeline, not the timeline of the maintainers. So to kind of look at all the kind of past and existing open source emulators out there, in the past, like nothing's really moved the needle since QEMU was released. QEMU released their architecture lifting and stuff, and they have their tiny code generator library, which is LGPL, so you can still link against it without having GPL infect your code base. And then recently, in the past few years, we've seen a lot of people start to use one of the popular disassembler frameworks released by NSA called Ghidra. They have an intermediate representation that they call P-code, and so people have started to kind of tie that in to some emulation capabilities. But kind of the problem with a lot of these, or some of the challenges at least, are that in some cases you release a really cool paper, like MetaEmu did a few years ago, but that was never released. That got stuck in embargoed on like getting open source approval, and we didn't get that. And also, a lot of the current libraries out there are mostly focused on either emulating target programs that are restricted to Linux and Linux user mode, or like in some cases with like QEMU or some Qeeling stuff, you get like other like Windows user mode and stuff like that. But like most things are focused on the general purpose operating systems. And when you are once you start to kind of ask the question of what do I do for my firmware for like this random device, or like some of like the sensors on like my smartwatch or something, like there's not really a good answer. And especially once you start to look at some of the old legacy processors and some old like Super H, some like TMS 320, really old family legacy DSP stuff, there's no answer. And so that's where Styx comes in. So we're kind of like, hey, this is our focus. This is a new option that when this is your target and nothing else supports it, Styx is ready to be there and ready to be the good answer. And we're working on it. So again, like Styx, inheriting from some of the things that I just said, like, oh, hey, there's challenges in these past technologies and stuff. Like, yeah, we also bring a little bit of some baggage. But the main things we're trying to solve here again is like the user configurability, some of the licensing challenges, and some of this old, like, there's just old forks of old tools and people released as a one-off thing, and it's not really going to work. And a lot of those kind of stem from working with QEMU, where they're like, hey, these are our limited processor sets that we support. These are the limited peripherals. You can make your own fork and use your own internal tools, but you can't make anything publicly, and it's not really that ergonomic for developers as like the users of these emulators to like extend. And then things start to get more complicated when it's like, what about if you have a SoC that has multiple processors? Especially if they're like different architectures and doing a bunch of crazy stuff, like what do you do? This is another, when people say, oh, why don't you want to use Unicorn to emulate stuff? This is one of my favorite examples. They have cleaned up a lot of the aborts in the code base recently. But if you can see here, do not call exit or abort to handle an error that can be triggered by user code. And so if you want to like write to some registers in Unicorn, it'll just abort, and good luck tracking it down. So coming back to kind of close up, hey, we had all these challenges and stuff, like what is Styx actually going to do? How does it do it? And like, where do we go from here? So again, like Styx, the main goal is to be a composable emulator. The nice thing about Styx is it's a bunch of interfaces. If you implement the interfaces, you can just swap out any of the components. It's great. And unlike a lot of the other answers here to the past of, hey, we have QEMU, Unicorn, Igloo, all these things, they're meant to run your software and not necessarily meant to debug it. So if you want your like instruction level fidelity on things, that's not really an option. Unless you want to like sacrifice a lot of the other niceties that they bring to the table. So like a lot of the other tools focus on like basic block fidelity, which could be groups of like one instruction to like groups of like 100 instructions, depending on like what architecture and some other things. But it's not always something that you or that fits your use case. So you need to be able to configure it. So yes, Styx, while it is a single thing, it is more of a library and collection of tools meant to help you solve your problems as the user and combine all the pieces and stuff you need, where if you do have a mainstream like Unicorn architecture, then you can use that backend if you want to like bring your own, like for a very specific use case, cool. If you want to target an architecture that is supported by like P code, you can do that. So yeah. This is, again, like, we just want to make one tool that does all the things. And if it doesn't do something, you can just do it yourself. And you're not stuck by the like potentially poor design decisions we made. So all that was just an introduction. So yeah, my name is Jordan, Lockbox. I used to do a lot of pwn and stuff, finding bugs in DSPs and other embedded systems. And now I make emulators. Because there's no tools if you want to like emulate a radio and find bugs in a radio or like the chips on this microphone. There's just not a good option. So yeah. Sorry, I totally mixed this up. Yeah, so to actually get kind of all this great stuff of, hey, look, this is just programmable and yada, yada, yada. We made a couple big design decisions at the beginning where we want to generate as much code as possible, meaning all the networking and connecting all the interfaces and peripherals to each other. If you want multiple processors, they just need to be able to talk. So we utilize gRPC to get a lot of that stuff done. And kind of over time, we have shifted from I just want to detect that a bug happened to now I want users to be able to debug any software, whether they're writing it or trying to find bugs and stuff. There's a little bit of a distinction. But yeah, so the main use case here for the Styx emulator is like when QEMU doesn't work. So QEMU, as I mentioned at the very beginning, it has like millions of man hours poured into it of, hey, I'm going to support all the things. It's great. But sometimes it doesn't. And a lot of times that is more pain than it's worth. And so what's the good option? What do you do? There's not really an option right now besides making a fork. And so now you can use Styx to help you debug your targets or to help debug your development tools, or debug your firmware that you're developing. And it shines really when you need to connect multiple emulators to each other or integrate with other external tools. So calling back out to integrate with physics simulators and GNU Radio, all that kind of just works due to the gRPC peripheral design, and that really makes it easy. So where like we being Styx Emulator is at today, this is a nice diagram of all the core interfaces in one pretty picture. The Styx repo, which I'm going to link here at the end, has tons of examples, extensive API documentation. While some of the user docs are out of date, the actual API documentation, so once you like open it in VS Code, you'll get nicely rendered user docs everywhere. There's a bunch of doc tests. That's kind of been the main resounding feedback I've gotten from people that have used Styx, is that the documentation is amazing, which is nice because I like nice docs. But yeah, so the main kind of abstraction here we have in Styx is we haven't really done much with the machine, so we kind of focus on the processor right now, where that's what people can kind of relate to as like, oh, if I have something in QEMU but it doesn't work, I need a new thing to support it. So that's where we make a new processor, and each processor can have like 0 to n cores, and each time you're working with the core and like doing hooks and stuff, talking with devices, you all get just a shared reference to all the internal state and event controller. And it kind of makes the ownership model very nice, and it makes it much more easy to kind of abstract. You're only working with one part of your system or another. Yeah. And then there's a nice, on the side, we have a trace bus and an IPC interconnect. Those are great for connecting multiple emulators together and also getting data and traces out of your system to actually see your data flow. So as like a minimal, absolute minimal example of little Rust library here, we have like 10 lines of code where it's like, cool, I want to build a processor. It's the specific ARM model, uses loader. I want to add some tracing, make a little function to get your firmware, and like you build it, and that's it. So that's, congrats, this is a Rust library. Yes, we use basic software architecture and software engineering skills, and now we can make a cute little API. Thankfully, there's also lots of nice bindings. So the equivalent Python thing is even less code, and it's like, again, like very simple. I'm going to speed through some examples here. One nice kind of usability feature is making integrated tests, a nice integration test between multiple emulators as you're developing your software. And so now you can, ta-da, a little bit nicer work than working with QEMU. So it kind of feels more like some of the existing functionality from like the Panda emulator, if you've used that before, or Chiling. Except now we're focused on like, congrats, this is like your embedded firmware, and you get the same tooling, same support, except now on all your legacy devices. So just an equivalent unit test example in Rust. Congrats, we can do testing. If you want to add a new target or ISA support to the Styx Emulator framework, like say there's something that's missing, there are like literal checklist examples and like checklist steps on how to do this. You can just go to the documentation site and it's like, cool, this is exactly the steps you need to do to add a new architecture to Styx, whether it's your own personal fork or it's the actual upstream one. If you want to add just new processor and like design your own that doesn't need to like patch anything with the Styx library proper, you can just do that. And again, like literal checklist examples here. And then sometime in the next couple weeks, I'll be finishing up a little blog post on how to emulate a TI-84, going from Styx doesn't know anything about this architecture, which is the Z80, to, hey, look, this is what it takes to add the architecture to Styx, to add all the register state, the CPU models, etc. And then, so that's like the Styx front end. And then adding the Z80 support to one of the backends that Styx supports. So going back a couple slides real quick. Right here, the CPU backend that we have under this processor core, kind of unique to Styx among all other emulation frameworks, is we have an abstraction over your instruction execution. So in QEMU, they only have TCG. In some of the other P-code examples, they only have their single one. Now it's just an abstraction. So if none of the backends inside of Styx actually support your target, but we have like the Styx front end support. So we've added architecture definitions and some of the register stuff, so you can actually read and write to it, just like all our other architectures. You can bring your own CPU backend, which is really nice for some of the like smaller, more bespoke architectures out there where like sometimes you might not want to publicly release an emulator for something. So now you can just kind of do that. And you can bring your own, and it also allows for nice specialization. Because right now, there are two in-tree backends inside of Styx. There's Unicorn, again, as I said, for kind of the mainstream stuff. But we also have a P-code interpreter, which is great for getting started and just like, cool, I just add it, cool, easy, new architecture. But it is pretty slow. Because again, it's an interpreter. But the goal here is just, you go from 0 to I have emulation of my target in as short amount of time as possible. And now once you have that, you can make your own specialized thing that only supports that specific target, or like only supports a specific architecture. And you can now make your own custom backend that does just the things you need to do without like having to do a bunch of invasive, crazy changes all across the code base. Because like the main problem here that is trying to address is like all of the old unmaintained QEMU forks for the specific thing. That's like, you don't need to do that anymore. So going back here, the current target support list that we have here. So for instruction set architectures that we've added and that Styx actually knows about, there's a bunch of the simple ones, like ARM32, 64, MIPS 3264. And then we kind of get to more the unsupported by anything area. So this PPC32 specifically is on like 20 years old PowerPC, which QEMU does not actually support. I checked, even though some of it's advertised. And then some more fun ones like Blackfin and Super H. Blackfin fan. And then recently, like within the past week, we just merged support for Qualcomm's Hexagon modems. So right now it's just executing code. There's no actual like built-in processor models for that yet. But again, like follow the checklist and you can just implement it yourself. And so there are people actively working on supporting the necessary peripherals to actually like store pre-built processor models in the Styx tree for all those Qualcomm modems. Um, yeah, it's same thing with all the peripherals and devices, where if you just want to add something for your own sake, you can just make your own local definition. And again, like it's all just writing to an interface. And so if you do want to eventually upstream like a peripheral interface or a device interface that we don't already have, you can do that. If not, you can keep it private, and your fork, well, you don't need to make a fork. That can just stay in your own private code base. That is the whole point of Styx, is to enable this like custom composability stuff. You shouldn't need to make invasive changes to a code base just to do the basic functions of your job. So like as some like more features and stuff that it exists, we have a built-in fuzzer and some other tools, but kind of notice for this Rust example, really the only difference here for some of these things I'm going to show is this executor option. I wish I would have highlighted it, but it's this whole middle area, and all of the like loaders and adding target programmer and stuff and which backend do you want to use, like those are kind of the same through all these examples here. The only thing that's changing is like add a new plugin, add a new executor, and it all just kind of like fits together. So again, like if you want a fuzzer, you can add a UI, and it just like that's included in the code base as an example. Looking at the debugger here again, like again, we just changed the same, like the only real difference here is like this one line. So in this case, this is just showing off like, yes, you can make, you can just run a debug server that controls the execution of this PowerPC target. Like that's really all that this is changing from like this fuzzer example to, oh, now I'm like fuzzing it to, hey, I'm now running a debug server and like specifically just to debug this target. Like that's really all it is. Because again, the custom composability. If you need it, cool. If you need the functionality, use it. If not, it can get compiled out. That's also like we have tunable tracing and introspection. So if you don't need the expensive like register tracing or memory tracing, you can just compile it out, and that's just not even going to be in there. So just as more examples, like we prepackaged some of the devices I talked about. This is like some ADCs, and I think one of these is a flash chip or something. And it's like to use them or just connect them to your processor. It's kind of really just this. The args here is just saying like, here is the like realized IP address of the processor that's running that you're connecting it to. And so programmatically, this is how it looks to just add new devices. It's really just simple. And then again, kind of what I've been talking and like kind of hinting about a lot is we have a really nice trace bus that you can just tune out and compile out the instrumentation you don't need. And you can connect multiple emulators to it at the same time. So one of the things that's really fun here is you now can track data across multiple interrupts, across multiple emulators by design. And that's just supported and it works because it should be something that just is supported and works, and you should be able to do it. And so congrats, you can do it. That being said, did realize that there is currently, this will be fixed very shortly because I realized this was a bug in this version. There is no way to tell what emulator the events come from. So that will be fixed soon. Sorry about that. But it does work. And it has been used to find some fun stuff. So, but again, like if you do like all these events are tunable. So see these register read and write events, those are incredibly expensive and will slow you down by like orders of magnitude. And so if you don't want those, I think these ones are actually disabled by default. So like, yeah, because otherwise, if you don't need all the expensive instrumentation, you should not be forced to pay the price to use it. Yeah, so now combining kind of all these like peripheral designs and, oh, hey, we have all these cool interfaces and yada, 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 and all this tracing, lets us do some fun stuff. So we have in the code base already, there's under our extensions subfolder, we have a MVP Ghidra data streaming library thing. So you can add it as an extension to Ghidra. It streams all your symbols and data type stuff to just like a centralized server, and then we have a web UI that will like show you the data structures changing over time that you have like defined. And combines like the trace bus with the orchestration piece with all the peripheral designs and the like processor interconnects and everything. It all just kind of is culminated in this single example. So now also you can say that like this emulator has microservices, which is pretty cursed, but if yep, it is what it is. Yeah, but that is again like the whole point of having like a simple unified like code base that we focus on having generated code at. Like if you just use something simple like gRPC, now any language that has a gRPC library can just talk to the processor, and can just talk to all these peripherals, and it's just easy. So yeah, so far it has been released for a little over a month now. I have a few DMs I get every week, some from the same people who are like fanatics. They're like, this is great. Oh my goodness. But those are like people who dove in, like had a very specific problem that they wanted to address. Like, you said all these things. This is what I'm looking for. I'm going to go use it right now. Like again, that's not for everyone. If like QEMU supports your use case perfectly fine, yes, please just go use QEMU. Like, please use the thing that suits your need the best. This is not like oh hey, go like drop everything and like go use Styx. It's cool. If you want to emulate a target for like AMD 64 or x86, that wasn't on our target support list by design. This has been requested to add it, so like we might, but again, like that's not like the goal here is to make yet another tool that supports and focuses on all the same commodity things that there's been like so much tooling around already. The point here is just to create like to raise the floor of tooling and debuggability on all the architectures at once. So it's like this is the minimum floor now. We just got to have like continue to raise the threshold and get better and better tooling, because like it's 2025. We should have nice things. So kind of taking that to the next step, like while there were people who were like, oh, this is great, like yada yada yada, there was like a couple questions where it's like, why not Renode, or why not this other emulator? Like, why would I use this or something else? And they're like, I just need to emulate Linux. I use this. Why should I use your thing? I was like, you shouldn't. If you have something that solves your use case, use it. This is here to provide a new option for a lot of the targets that traditionally you've been stuck using, like the TI simulator that will just like break when you're like running like the hello world, or like try and integrate with their like little JScript hooks. Like, good luck. But like some of the other things where it's like, hey, you need to make some improvements, where it's like it's not that easy to make new components. I had to like look at the examples and stuff to look at the code, and there's not like a simple way to just copy and paste the like necessary skeleton code, because it's like you have to implement the trait stuff and then connect it to the rest of the library. And they're like, yeah, like why can't you just auto generate it? Which we'll get to that. That has been addressed already. And then we, as the Styx emulator group team, Styx emulator library contributors, etc., there is no registry like packager. You can't pip install Styx emulator. You can't cargo install it. Right now it is just a library. We're still figuring out what a binary installable version of Styx should look like, and what kind of options. Because again, if the whole point is to be a like user tailorable thing, like that's a combinatorial explosion problem of like what features do you turn on by default and stuff. So we're figuring it out. We'll get there eventually, but we're not exactly there. So for addressing the new components, there's on the documentation update MR that is still in progress on the code base. There's a fun little commit. If you want, you can check it out. It basically gets you a bunch of pre-canned auto-generated stuff, so you can like literally type cargo generate, and then you point at the thing, and it'll just ask you a bunch of questions, and then it will generate the proper code at the proper location, and now you can just get started. It's like if you want to make a new processor, cargo generate new processor, boom, done. You can like cargo generate peripheral, whatever. And then it'll set up all the initial skeleton stuff for you, just to make that easier. Because again, like it's 2025, things should be a little bit better. Yeah. So kind of now shifting focus to all the stuff we already have, or all the features and stuff like we've done. Now this is like the current development, and then kind of like what's next, and some other fun ideas and stuff. So right now, again, like we just merged Hexagon, and so there's going to be some more progress there. The documentation stuff with the auto-generating components. And then something we're starting to think about now is how do we, moving on from just an emulator, like we want to make it easier to debug stuff. That's really the main goal. As like an attacker trying to find bugs on these systems, you're like, wow, these debug tools suck. Like, why can't I just build code for this thing? It turns out on the developer side, the tools suck and it's really hard developing code for this thing. And so they kind of really just want the same thing, which is better debugability and better introspection into these systems. And so working right now, I'm kind of like working, collaborating with some developers, some attackers. We're trying to come up with what would it look like as like a nice new ideal remote debugger interface. And so using Styx as an exemplar, we're like, hey, what if we do this? Yeah. And so hopefully it goes somewhere. It's pretty cool. So looking at kind of the current development efforts, Hexagon again, just merged, new specific SOC support coming soon. Right now, just focusing on the modems, not on any of their GPUs or AI neural processor units, I think is what they call them. Yeah. So one thing about the Hexagon support is that so far, that was the longest it has taken to go from 0 to executing code in Styx, which was 3 months. I did the whole Super H family in a few hours, like Super H 1, 2, 3, 4, and like all the extensions. I'm just adding like the Slay architecture and stuff. But this Hexagon support, because it's so complicated, and it was a new like execution paradigm where they have instruction packets, it took a couple months and a lot of back and forth and stuff. Yeah, very complicated. We have more complicated architectures in the pipeline, so stay tuned. Documentation MR, again, auto-generating stuff. And then there's, if you look at some of the documentation site right now, it'll say like TBD or this needs to be rewritten, et cetera, et cetera. All of those are currently rewritten, and then we're just working on a general refresh overall. So if you do need some documentation or like, this looks a little wonky or I wish there was more, I would check out this MR real quick. It should be addressing a lot of those needs. Yeah, so talking about the debugger, we are, like the exemplar case here is going to be making a Binary Ninja debugger backend for the Styx emulator. So now if you're like reversing some firmware in Binary Ninja or whatever, you can just use Binary Ninja debugger UI. And it's like nice, pretty UI with like our execution backend. So now you can get the high fidelity emulation. I think they're also working on emulating their MLIL or something like that with Binary Ninja. That's considered like low fidelity, where it's like kind of ignoring a lot of the semantics of the underlying architecture. This is not that. This is a completely different effort. We are just focused on high fidelity emulation with Styx. Happens to be using Binary Ninja as a pretty UI. And then one of the things I didn't really touch on too much was the unified configuration. So unfortunately, YAML's kind of used everywhere. However, there's lots of nice things you can do once you have a single like serialization format of like your configuration, which YAML's actually really good at. And there's a lot of really well-tested libraries all over the place. And so now, kind of thinking towards what would a single installable version of Styx look like, it would be really nice to have a configuration file. Like if you think about using QEMU, if you've done that before, sometimes your command line arguments you pass it are a little insane. And a few hundred lines of just options later, you're like, okay, I guess I'm finally done. So now you kind of do the same, except now you have like a typed YAML schema, and you can either use command line options, configuration file, environment variables, whatever, to override it. So like here's an example, we're like using the P-code backend for some PowerPC stuff. We're going to run it under GDB, so very similar, like this is literally the exact GDB debugger example I showed earlier. And then just this is how you load the file, and then ta-da, I'm also gonna like set some registers up by default. So like it's pretty straightforward, pretty easy, just gets it all done, because it should be easy. And then upcoming development. So things that are also just missing in general from QEMU is like the embedded soft MMU having hypervisor support. Those extensions just aren't really supported. And there's been a couple people that have asked, well, since it would take a lot of work in Kimu, why don't I just have someone implement it in Styx? So there's some people doing that now. Condolences. But yeah, it'll be really cool. Because now a lot of the kind of tracing events we have, a lot of the tooling and stuff will kind of get flipped on its head because we didn't plan for this. We didn't plan for supporting targets that had hypervisor support. So now this will be kind of adding even more stuff to the possible abstractions and configuration files and interfaces and stuff. And so now we kind of will get like a really nice modern kind of like software abstraction look at what these complex computers look like, which hasn't really been done before, which is cool. And then some other stuff people are working on, bring your own or pick your own Android phone emulator. So kind of taking this ARM64 hypervisor stuff hand in hand. Now, if you want like a different phone with a specific SoC, if Styx supports it, you can use that, wire it up over like PCIe or like direct memory as an example to like your specific modems because we just added hexagon support. Or like say like you wanted some MIPS stuff with like MediaTek or something. Like now, like not now, but in the future, that is something that will be possible. Where like with a single configuration file, congrats, this is now like a Samsung S25 or something. Just by design, and it all just fits together. Also coming up shortly, I have a bunch of these TMS 320s in my basement that I need to debug for reasons, and so I'm going to start adding this architecture. If anyone else wants to add any more TMS architectures, I'm all for it. I know you specifically are interested in it, and a couple other people. So let's do it. And then taking the configuration and stuff one step further, it is very easy to reason about a single installable daemon or something. Like that's something that like Linux packages like do all the time, or like if you're gonna go run something in the background and then connect to like a remote server to spawn you something, like that is easier to reason about than necessarily like here's a local emulator you just run. So we are looking and very interested in creating a remote orchestration setup for the Styx emulator. And then one of the last things that's upcoming that we currently have pretty good plans about is device tree driven emulation. So right now in Kimu, if you want to emulate something, it will like override the device tree by default in Linux, and it'll be like, cool, here's the drivers that like Kimu itself is giving it. But sometimes like things need that specific hardware and you can't get away with that. So now Styx being like more of a hardware first approach to emulation, where you emulate the hardware and then all the software that uses that should just work. Yeah, that is the goal there, to create like the automatic emulation. Which yeah, that's a funny term that doesn't really mean anything. But like now you can kind of say, hey, all natural, like with all the artifacts from this actual device, you can create like a true, like no shit, full system emulator for this target. Yeah. So some other fun research ideas. We have pretty cool trace bus. You can make trace analysis great again. It was all the rage for a few years and it's kind of fallen off. We could do that. Bunch of people have been asking about time travel debugging. We have a mostly deterministic emulator, so we haven't really had a need for that yet. But we will eventually, right? So how to do time travel right with like a single interface over multiple complex different systems. That's a complicated topic. And then kind of going hand in hand with the time travel, the cross emulator time synchronization. Right now, we just kind of wing it and call it good. For a lot of these simple targets, it works, but once it gets more complex, that's not an option. And there's a couple people here at this conference already have mentioned, like, we need a new sleigh for Ghidra. There's a lot of issues with it. If you're interested, come talk to me. I think we should probably make like a mailing list because there's so many people that are interested in this. The important thing here is going to be like backwards compatibility with modern sleigh. And so like now you can like lower from this new thing into sleigh. Yeah. And then other fun ideas, more stuff. If you want to do stuff, got plenty of ideas. If any of these ideas are something you were thinking about, do it with Styx. It'll be great. I promise. Yeah. So in summary, Styx Emulator, new user configurable emulator, designed to be extendable by users, designed to integrate with other tools using a single interface. Should always be the same. You shouldn't need to rewrite new tools just because some implementation detail is slightly different than something you already are looking at. And yeah, so thank you.